Swayam Prabha. Digital India. Educated India.
Okay, good morning. So, in this class, I want to discuss about another application of continuous Markov process from the Fokker-Planck framework. This is to do with finding out the rate constant of a process where there is an energy barrier separating two states. Let's say you have state A and state B, and there is an energy barrier over this. And you want to look at what rate this transition from A to B happens. Okay. This kind of processes is very relevant for chemical engineering, physical chemistry, and some physics also. If you were to think about a reaction A going to B, we know that there is a potential energy difference between the two states A and B, and there is usually an activation energy barrier. This activation energy barrier comes in the reaction engineering case where bonds have to be broken, bonds have to be formed. Okay, so there is an associated activation energy barrier. There are other problems where, for example, you want to look at some phase transition. Let's say you have a supersaturated vapor, and you cool this, and then it becomes a liquid. Okay, so this gas to liquid or vapor to liquid transition also goes through an energy barrier. Or if you think about a polymer molecule which goes from one state to another state, more from a folded state to an unfolded state. Similarly, protein. There are many such problems we can encounter where the two states are separated by an energy barrier. And a theoretical framework that allows us to calculate the rates of this transition is very important, and we can apply the continuous Markov process or the Brownian motion over a potential well as a starting point. Of course, with making some simplifying assumptions, we can get a kind of a closed form of solution, purely analytical. And you will see in reality, when you apply this theory, there will be a lot of challenges because of the oversimplifying assumptions. But this kind of sets a starting point from many other advanced theories. Okay, so this was done by Kramer. It's known as Kramer's theory, 1940. We will look at that problem and then look at how to calculate the rate constant. Okay, so the problem in hand is you have a potential. Okay, so let's say there is some state A and there is some state B. Okay, so and then there is this energy barrier here. Okay, so you start with certain molecules here, right? So we start with a certain number of molecules. This can be a reactant, and then there is another energy state which is lower than this energy. Okay, so here the y-axis is the potential energy. So if you consider this is 0, this is a negative value, so this is more stable. So the molecule wants to actually go from here to here, but they cannot go directly, it has to go over this barrier. So the mechanism by which they can do is a slow diffusive process. The particles want to climb this mountain, the barrier. Once they reach this mountain, they can fall. Okay, so the mechanism by which the molecules can actually make a transition is through a diffusive process. Okay, but this diffusion happens over a potential energy barrier. Now, if this barrier height is high enough, then the number of particles going through this is going to be very low. Okay, because the barrier is so high, scaling this big mountain is very difficult. So very few number of molecules will execute this random motion. So most of the time the particle will move and then come back. They move up and then come back because they're a random walk, okay, against a potential well. but then if you wait long enough, few molecules will make this transition. Okay. So, and then once the particle comes here, then they are removed from the system. Okay. So, we want to find out at what rate the particles are transiting. Okay. Like I said, this state A can be a reactant, potential energy of a reactant, and this can be potential energy of a product, or it could be a metastable liquid, sorry, metastable vapor, and this wants to condense into a liquid, or it can be a polymer in a coil form, and then it wants to get folded. You get a folded state. Okay. So, there are many such problems where there are two states separated by an energy barrier. Okay. So, we call this energy barrier height here is Q. This is not the energy barrier, only this. Okay. Because starting from here, if it scales this energy barrier, then it can come down. Okay. So, we want to basically set up a Fokker-Planck equation for this problem, and then we try to calculate the rate of this transition. So, in doing so, I will inform many such many assumptions, but the bottom line is we are treating this process as a Brownian walk, Brownian random walk in one dimension. We will take this x as the one dimension, and then we will also assume that the particles are not interacting, so that you do not have to worry about how particles are interacting. But in general, there is going to be some sort of an interaction between the particles also. Okay. But for now, we will think of a non-interacting particles executing a one-dimensional random walk over a potential energy barrier. So, that is a problem. Okay. So, assumptions. We say initially an ensemble of particles, we will say ensemble of non-interacting particles. Present in the basin A. Okay, that is the starting point. We say the problem is one dimensional. Over a barrier. And then we see that this barrier height, which is Q, is much higher than thermal energy. If this condition is not there, what will happen is, if the barrier is very small comparable to thermal energy, you will see that quickly all the particles will actually go to this. Okay. So, there is going to be a very fast rate. Then the approach that I am going to discuss will not be possible. So, here we make this barrier so high that the particles have to diffuse through this, okay, no matter what the initial velocity distribution is. On the other hand, if you have Q comparable to kBt, those molecules which has the initial kinetic energy or initial velocity will directly go here, okay, and the diffusion may not be a right mechanism there. It is going to be more like a ballistic motion. But by keeping this Q very high, we actually remove that choice and then we say that the process is completely a diffusive process. So, the strategy to calculate the rate of escape K from A to B, we define as the flux J divided by the number density of molecules at A. So, J here is the flux of particle crossing this barrier, okay, divided by the number density of particles starting from here. Okay. Generally, we write J equal to K times Na. I am rewriting this into a definition. So, now what we need to do, we have to find the diffusion flux by solving the Fokker-Planck equation for this problem, and then the number density of particle in A. Okay. Once we do that, then we can find the rate. So this is our definition of the rate constant K. So now to find the flux J, this is a diffusion flux. We have to cast this problem into a Fokker-Planck equation. So we have this dou P by dou T is equal to minus dou by dou X AP plus 1 by 2 okay. So now for this problem we need to find what are the characteristic constants A and B. So clearly B is 2D because it's a one-dimensional random walk. Okay, constant B is this. A, which is kind of representing the drift. To find the expression for A, what we will do is we will first write this problem in a Langevin dynamics and then look at what the drift term is. Okay, so in this case we have Langevin equation. If I think about one single particle and look at the dynamics, we approach this problem through Langevin dynamics. So we say that this mass times the second derivative of position is equal to the sum of the forces. So what are the forces? We have the drag force, and then remember this is a random walk over a potential barrier. Okay, so the force acting on this is going to be the negative of the gradient of the potential. Okay, so it's going to be minus du by dx, where u is a function that describes this potential, okay, which is an one-dimensional potential. So this derivative will give you the force, and then you have this diffusion thermal noise, which is 2 gamma kT into eta t. Okay, so this is our Langevin dynamics. So the mass times acceleration is balanced by drag, the potential gradient, which is the force acting on this particle due to the potential. When there is no potential, this is 0, then we have a free Brownian particle. We have seen some other cases where there was a gravitational force, there was a spring attached to that. So there are different kinds of force you can add here. Okay, and this is the thermal noise. So we will say that this is an overdamped limit, where we say that the mass times acceleration is 0. So then all the forces are in balance. Okay, so we write that gamma times dx by dt is equal to minus du by dx plus square root of 2 gamma kt into eta t. Or we say that dx by dt is equal to minus 1 by gamma du by dx plus 2d. Okay. So now this term dx by dt tells me the rate of change of particle position of a Brownian particle walking in a barrier. So this term, first term that you see here, characterizes the drift, and this one the diffusion. Okay. So we already know that B is 2D and A is going to be minus 1 by gamma, the gradient of the potential. Okay, so I know characteristic functions A and B. Okay, so now I can substitute here. Note that I have not given the functional form of u yet. Okay, so u is the total potential for the entire range of x. So we have not given the actual functional form. So until then, we will just keep this as a derivative as such. So here you have okay. So this is our Fokker-Planck equation. So note that this P here is representing the position of a Brownian particle as a function of time. Okay, so probability density for a particle position x at time t for a Brownian particle undergoing a one-dimensional random walk in the potential. So now what we will do is we will assume a quasi-steady state where this time derivative goes to 0, assuming quasi-steady state where the partial derivative goes to 0. So what this basically means is when the number of particles overcoming this barrier is very few. Whenever a particle go this side, they are basically absorbed here. Okay. Now, when one particle does that, you will actually put another particle here so that you keep the number of particles in the basin always the same. Okay. So therefore, in that kind of a condition, when you have a reservoir having constant number of particles, you can assume this state to be a quasi-steady state. Okay. So the flux of particle going through that will has to be that's going to be constant. That's what I'm going to see. So we will see that the time derivative is set to 0. So we have 1 by gamma d by dx is equal to 0. Or we can write this as d by dx of 1 by gamma du dx p plus d dp by dx. And we denote this is the flux. In fact, if you go to the original equation, you can actually show this is equal to dou p by dou x, dou p by dou t is equal to dou by dou x of j. Okay, so this entire term that you see here, that's a flux. We are saying the derivative of the flux is equal to 0, so that means j is constant. The flux is constant across this. Is constant. Yeah. So what I'm saying is here that even though initially you start with certain number of particles and very randomly the particles are diffusing and then they cross. Okay. So if they do that, you will see that the number of particles in this case gets depleted. Then in the future, the number of particles that will cross this will get changed with respect to time. Okay. So if you want to make an assumption of a quasi-steady state where we can analytically track this problem, we'll have to replenish this loss of particles whenever there is a transition. So at every time the number of particles in the reservoir is the same, so we can expect that the flux of particle going through this barrier will remain constant, quasi constant. So that's the assumption that I'm making here, where then the probability distribution function will become independent of time. Okay, so that's the assumption that we are making. So that is not strictly valid. Like I said, to analytically track this problem, we make these assumptions. Yeah. One more thing I have to do here is, so this is valid. We have to say this is equal to minus dou j by dou x. So j will become minus here, minus here, minus 1 gamma. So now we will rewrite this equation. So what we have written in expanded form can be written in more condensed form. So suppose if you open this up, if you do this, if you apply chain rule and open this up, you will see that this expression and this expressions are actually equivalent. Okay, and here we see this beta here is 1 over kt, and yeah, the remaining things are already defined. So bringing this to the other side, j times e power beta u, you get minus d d by dx of p into e power beta u. So I already mentioned that j is constant because we are looking at a quasi-steady state conditions. So now what we will do is we will integrate this expression from the range a to b. So we say that j integrate from a to b. When I say a to b, I mean x going from a to b. Okay, e power beta u. Remember, u is a potential that changes with respect to x, so it remains inside the integral. And here I have minus d integral a to b d by dx of p into e power beta u dx. So here when I integrate this d by dx of p e power beta u dx, I have to estimate this p times e power beta u at two limits b and a. So pb basically means the probability function measured at x equal to b, that's here, times e power beta ub, the potential at here, that's ub, minus pa, that is a probability at location a, times e power beta ua. Ua here is a potential. Actually here the potential is 0 in this particular reference. So here what we'll assume is, we'll assume that PB is 0. Why we say PB is 0? Because this energy well is so deep, if a particle actually crosses, it's never going to come back. There is no reversible, there is no reversible transition. It's a irreversible transition. So this is a deep well. So a particle that is going to base in B not going to come back. So the probability of finding a particle here is actually taken out of the system. So that is 0. And then UA is 0 because that's our reference potential. With respect to here, the energy barrier is Q. Okay. So if you substitute all this, you will see J is equal to, so this is 0. So here I have one minus PA. So it will become D times PA. So we get the flux as given as d PA by integral A to B e power beta u dx. Now, if you want to go from here, now we need to specify the functional form of u, only then this integral can be calculated. Okay. So what is usually done here is, we look at the functional form here. We will assume that the potential here can be approximated as a parabolic quadratic form. So we can actually write around here, we can expand the potential and then substitute that u here. So you can analytically solve this integral. If PB is not so it's gonna, you're gonna keep dealing with the other extra term. So I'm talking about the original Kramer's theory where this assumption was made. If this is not so deep, if it's gonna be reversible, that term you cannot basically neglect. You have to keep working with that expression also. So around C, around XC, so this is the location of XC, we approximate the potential U of X So we are saying the potential around x equal to xc, around here, we approximate this potential as a quadratic term. Okay. So the q here is the barrier, okay, and this wc squared, this is basically the quantity that tells you the spread of this, how steep it is. Okay, it tells you the spring constant kind of thing, and x minus x squared is a quadratic term. Okay, it's a symmetric about x equal to xc. Okay. So generally we say that the potential we generally write like this, where u is equal to half k x square. Now the potential is inverted, okay, and that's why I am writing in this form. So now what we can do, once we approximate the potential, and then this integral can be centered around here because this potential is the highest one. So I already mentioned that this potential is very high. So we can integrate this function using this u, and if you do that, I will skip the terms here. You will see that the integral of a to b, substitute u from here and then integrate from a to b, you will get e power beta q to pi kt. So now we can substitute for j there. So j will become d pa over square root of 2 pi kt omega c e power minus beta q. So clearly you can see this flux here depends on exponential of minus beta q. If this barrier is very high, you can see flux is exponentially decaying. That means the number of particles crossing per unit area is going to be very, very small because of exponential dependence. So now we got the expression for flux J, and to calculate K, the rate constant, which we defined as J by Na. Okay, so to find Na, we again get Pa e power minus beta u dx. So now what we need is to get the number of particles in this zone, in this basin. Okay, we integrate around A, around point A here, we integrate Pa times e power minus beta u dx. So here again u is the potential around this point. Okay, so this also we will assume this to be a harmonic or a quadratic potential. So we say that u of x is equal to 1 by 2 omega a squared x minus, I think we just put x squared here, that is it. So when we integrate this, you will get Na as Pa by Wa square root of 2 pi kt. So we have got both the number concentration of particle in basin A as well as the flux of particle crossing this barrier. So substituting that in K, you will get dPa omega c e power minus beta q over 2 pi kt. Okay, so this is J, and then now we divide this with Na here. So Pa cancels, you get d omega a omega c e power minus beta q by 2 pi kt. So the rate constant A to B is proportional to the exponential of minus beta q. So if you look at this expression, this is very similar to the Arrhenius formula. Arrhenius formula we use for rate constant. We have a prefactor and then we have this energy barrier factor. So you can see a similar formula, but the prefactor that you see here, that is the diffusivity and the curvature of the potential omega A, omega C, and then the temperature. These will tell you the prefactors. Generally, we do empirically, we try to calculate the prefactor, but here what we are saying is, if the mechanism of transition is purely diffusive, then you can actually get the prefactor that depends on the diffusivity, the potential width, okay, that governs the potential around A and C, and then also the temperature. And of course, this energy barrier will tell you how strongly the rate is dependent on that. Okay. Now this theory is very, very primitive, because as you can see how many number of assumptions we have made. But even if you remove some of the assumptions, okay, what will happen is there is going to be only some correction factor you will see, okay. Some correction will happen here, but the dependence of these variables on the rate remains the same, okay. We separately published a paper where we didn't look at this potential, we had a slightly different kind of potential called Lennard-Jones potential, and we did the same theory, and what we found was the only change from Kramer's theory is only a prefactor, okay. So that can be of the order of 1 or maybe less than 1, okay. So the beauty of this model is that despite that so many assumptions we made, quasi-steady state, one-dimensional, diffusion controlled, barrier being very high compared to the temperature, notwithstanding all these assumptions, the final expression is not very different even if you include those additional features, okay. So that's why this theory was very powerful. It was built in 1940. Even today you see that when you try to reconcile your experimental data, the first thing you do is to try to express from Kramer's theory. In my class notes, I have given some additional references where you will find applications of this Kramer's theory for protein folding problems, reaction dynamics, polymer folding problems, and so on. So it's a very powerful method, and I wanted to discuss this because you can see the simple Brownian random walk that we talked about can actually give us very rich information about the rate transitions, okay. I wish I can do more such transition problems, but I think we are close to the end of the course. So take this as an example and then explore more if you like, yeah. So I have skipped some of the integration steps in between to save time, but all these details are there in my notes, so you can work it out and see for yourself, yeah. Okay, so we'll stop with that. Any questions, any comments for this?